So in this video, I would like to talk about elastic beam theory. So here we have a beam segment and some loading. Okay, so the beam will deform like this. So this is exaggerate shape. So the deformation will be very small, but for demonstration, we draw the deformed shape like this. So let's take a look at a very small section, very small segment. So this small part will deform like this. Okay. So if we enlarge this small rectangular section, we can draw here. So this is a small section. So we say the dimension is dx. So the dimension is dx. So along this beam, we need to define a neutral axis. So neutral axis is that. Neutral axis is that. On this axis, there's no deformation. So we draw the neutral axis like this. So on this neutral axis, there's no deformation. So above this neutral axis, the beam will be in compression. Below this neutral axis, the part of the beam will in tension. And along this neutral axis, there's no deformation. So that means there's no compression or tension. So for this rectangular section, the neutral axis we put over here. So along the neutral axis, dimension is dx as well. So this is the segment before deformation. So now I would like to draw a segment after deformation. So it's this segment. Okay. So now the neutral axis, there's no deformation. See, if there's no deformation, the neutral axis still have length of dx. If we find an arbitrary line over here, we call this line is ds, have length of dx. So before deformation, ds is equal to dx. And if we set up a coordinate systems, so this is y, the x-axis is along the neutral axis x, so we say the distance between ds and dx is y. So as we know, the ds is above the neutral axis, so the ds will be shorter. Dx will be shorter, so we call this is ds prime. So as we know, these are circular arc. So for circular arc, they have a center. So they have a center. So suppose the center is over here. So the center of this arc is O. So from the center, the distance from the center to the arc is radius of curvature. Radius of curvature. We using a Greek letter rho to denote the radius curvature. So the O is center of curvature. So O is center of curvature, rho is radius curvature. So the distance between O to dx is rho, and we know the distance between ds and dx is y. So we put over here, so it's y. So it's y. Then we know the distance between O to dx prime. O to dx prime is rho minus y. Okay? So suppose the angle of this arc is d theta. So from this geometric information, we can derive that the ds prime equal to the distance between the center to the arc is rho minus y times the angle d theta. So once we know the ds prime, we know there's some change between ds prime and ds. So we can calculate the change between ds prime to ds. Okay, ds prime is rho minus y d theta. And ds, we know ds is equal to dx. Okay, so from this, we also know ds is equal to rho times d theta. So we can just plug in dx over here, then we can come out rho minus y d theta. So this is dx prime minus dx. dx is rho times d theta. Okay, so then we have, if we can cancel these two, rho d theta, cancel these two, we have minus y d theta. So this is the change between the ds prime to ds. So based on this difference, based on this change, we can derive the strain. As we know, the strain epsilon is equal to the difference between between the deformed shape and undeformed shape, ds prime to ds over ds. Okay, is equal to, we're plugging over here, minus y d theta over ds. ds is over dx. dx is equal to rho d theta. Then we can derive, we cancel d theta, we derive y over rho. Rho is the radius of curvature. So we come out this information. The strain along this line is equal to the y over the curvature. Y is the distance between neutral axis to the line we are studying now. So since it's elastic beam theory, so for elastic beam theory, we know there's a Hooke's law can be applied to elastic beam theory. Hooke's law tells us that the strain epsilon times the Young's modulus E is equal to the stress sigma. So this is Hooke's law. So based on Hooke's law, we know the strain epsilon is equal to minus y over rho. So then we can derive the stress equal to minus EY over rho. So now we have derived the relationship between stress and the geometric information, the radius of curvature, the distance between the line, we studied to the neutral axis. So then if we find the stress, if we can express the stress with the internal bending moment, then if we can find a stress with the internal bending moment. So then we can find the relationship between the internal bending moment with the geometry information. So we will talk about it in the second part of this video. So we'll see you later. Thanks.